going to talk about and derive the harmonic addition and subtraction formulas for trigonometry today. Here is what they essentially are. They're basically, if you have a linear combination of sine and cosine terms, and you want to express them purely in terms of a cosine or a sine term. Now for this derivation, we will consider cosine only, but the final product we should get in the end is the following. A of theta times sine to the n theta plus b of theta times cosine to the n theta, where a of theta and b of theta are components of one particular vector, and then r of theta is some radius, which we will parameterize, and then finally cosine of theta minus alpha is the difference in angles between these particular vectors. So I've listed here to remind you for the simplest example what a linear combination is. Let C1 and C2 be scalars in the field that you're considering with, V1 and V2 being the vectors in said vector space. What you simply do is just take each of these components and multiply them with each other for its corresponding index and then add them together. So W equals C1 V1 plus C2 V2. And in this case, it works here as well, in this format, and we have two quantities that we need to parameterize to find explicitly. I don't list it here because it's going to be very tedious doing all the grunt work before you show the final result. But what we need to go and find right now is the magnitude or the length of the vector, of the final vector, dot product, and then the angle between the dot product. Those are two key important things we need to find, which are r theta here and alpha here. And note r theta is just a quick usage of the Pythagorean theorem. Alpha here is just taking the angle between the rise over run of a function, of an angular function on an Argon diagram, or on a, computer just acted weird a bit there. On a diagram where you let the x-axis be the angle, basically cosine of the angle, I should say, pardon, and then the y-axis be the sine of the angle between them. Yep. So to get this, we are going to have to beat the dot product to death. And here's the two relevant vectors we'll consider. So again, here's how you reminder of how the dot product works. You're given, in the simplest case, a vector of two components, say u1, u2, and then another second vector, v1, v2. The algebra expression for the dot product is to simply, as I said, take each of these components, multiply them by each other, and then add them up, as over here. But there's also a trigonometric or geometric expression for the dot product, which is to simply take the product of their lengths, as well as multiply by the cosine of the angle between these two vectors, u and v. Now, finding the angle between u and v is something that is non-trivial and might require some stating out, and oops, the computer cut out my little, okay, there we go. So that's what would be the vector length or magnitude. But we can define alpha. Let's define alpha to be basically an angle greater than 0, and then theta to be an angle that's bigger than alpha. So then alpha will be given by this purple subtended arc over here. Whereas theta would be, and I didn't write theta here or it got cut off in my prep work, theta would be this green arc over here for this subtended angle. And then to find the angle between them, you would have to subtract the greatest angle minus the smallest angle, which would give us this red quantity theta minus alpha here. And then I have a of theta, b of theta, and then I have sine of n to the theta and cosine of n to the theta, where n is basically any, pardon, something stuck in my throat, n is any integer. because basically we want to generalize this to work for any kind of identity or power of sine and cosine, which would correspond to some placement when rotating clockwise or counterclockwise within the Argon diagram. So we want to be able to rotate forwards and backwards. Now, with that being said, let's go and put this to work. Finding the algebra expression of the dot product is easy. Just get this, multiply by this here at the top, and this at the bottom, multiply by this at the bottom here. You get this result on the left-hand side. And on the right-hand side, we take the magnitude of this quantity here. That's very easy. You just express it like this. And then on the right-hand side, we put in this quantity here. So we get sine of n theta being squared, same with the cosine of n theta. And very luckily enough, because of the Pythagorean identity, which is basically that sine squared theta plus cosine squared theta equals 1 for any angle theta. That's the key thing about identity. An identity is essentially an equation where both sides of the equation are necessarily true for any universe you're dealing with. And given this stuff basically cancels out to 1. So indeed, the radius or length of the vector or dot product we're dealing with is indeed square root of a theta squared plus b theta squared, as we wanted. But we have to go and do some other finessing of this formula here to go and help us find the angle, which is not that easy. So over here where we have cosine of theta minus alpha, we're going to use the compound angle formula for cosine, which you could see derived in many visual proof videos of trigonometry at this point, or I might do one later on in the future. But basically, this difference can be expressed, well, technically you consider it the sum, and then like put in a negative angle, but it would always be cosine of theta plus alpha equals cosine theta cosine alpha minus sine of theta sine of alpha. And then if you're going to plug in a negative angle, say here, you're going to have to plug in negative angles for these inputs, hence why we have a cosine of negative alpha here. Let me go and shade this in. And a sine of negative alpha here. Now, in the next line, we basically consider the fact that cosine is an even function and sine is an odd function. So because of that, we get that cosine of negative theta equals cosine of theta, sine of negative alpha equals sine of theta. We have these things here. And now, just to simplify so we don't have to write a bunch of stuff, we're going to substitute this back as r theta here. And now how we parameterize the angle, as seen over here, is to go and basically split this up into a product of two terms, and then we're going to match them up. Go play match the terms, match the puzzle pieces, so forth. So then this guy over here, oops, sorry, that was for the entire thing. In fact, I think it's going to, okay, resort. So like this over here, this term over here matches up with this term. Oh, sorry, we want the sines. Basically, the sines will match up with each other, and the cosine terms will match up with each other. So then this goes with the sine term here, and then the cosines match up with each other. So let's consider this particular inequality. And now we're going to go and parameterize for sine of n theta by dividing both sides by a of theta. Similarly, we're going to do that with cosine of n theta, which we get once we divide cosine of theta to the n by a single cosine. You get cosine to the n minus 1 theta. Actually, yeah, shouldn't I have something different in that regard? Yep, I made an error. My apologies. There should be sine to the n minus 1 theta. And similarly, we can do it with cosine of n to the theta as well. But now note that the original parameterization that we want to find for the angle, right? We always do tangent of the angle, right? So how can we end up getting like tangent? Well, we simply get sine over cosine. Use the identity that tangent x, or tangent of theta, equals sine of x over cosine of x. Okay, now I have to split this up here. And so, oh, okay, that's why I didn't like make the parameterization there. In the end, when you're doing tangent of n to the theta, you're basically going to have to go and like get this term over here divided by this term over here. And I just consider it like it's two fractions, so we'll do one fraction divided by another fraction, so you get one fraction and multiply by the reciprocal of it. And when matched up this way, you're going to get a single tangent of theta, a single tangent of alpha, and then you replug in back in what your a of theta and b of theta are. Actually, no. A of theta and b of theta are given, so that's whatever function or input you put in there. Given that, we do a bit of cross multiplication here, b of theta, a of theta here, and then cross multiply to the other side. We can divide both sides by tangent theta to get rid of one theta here, and we get the final result that alpha equals inverse tangent of a of theta over b of theta times tangent to the n minus 1, the n minus first power of tangent of theta. And also note, this formula also works depending if you're having a plus or minus. You just have to keep note of the sign convention you're using and determine whether you're rotating clockwise or counterclockwise. So in conclusion, this is the final formula for harmonic addition and subtraction for trigonometric functions.